noteworthy that most of the major cancers are really diseases of aging. And about 5 years or so ago, the National Cancer Institute and the National Institute on Aging observed the fact that of the 65 or so comprehensive cancer centers in the country, only one had a program on aging. So they wanted to jumpstart research at the interface of cancer and aging to learn about the underlying molecular mechanisms that predispose older organisms to develop cancer, and also to extend this kind of work at the epidemiologic level and also at the clinical level to get geriatricians and oncologists to work together and to have geriatricians get advanced training in oncology. So this, I think, echoes your thought about how to proceed.
Right. I mean, it's also fair to say this is not an easy topic to study in human beings, but I think you were about to say the sorts of new tools and ways of thinking about it that perhaps means that there'll be more rapid progress in the future.
Well, actually, I think it's useful to understand the implications of what we're talking about here. We're willing to spend an enormous sum of money with chemotherapy, radiation therapy treating cancer. We're willing to spend a lot of money putting stents in people's coronary arteries. We spend an enormous sum of money on pharmaceuticals, all designed to treat disease, to extend life. What these scientists are talking about is a single intervention that has the potential to simultaneously postpone and significantly delay all of the diseases and disorders associated with aging simultaneously. It would be a single event with a major breakthrough against all of these diseases. It's extraordinarily exciting.
Okay, let me just ask this one thing, and any of you jump in. Back to the point Dr. Butler was making, I mean, should this be almost like a major sort of mega push?
Yes. We really couldn't have anticipated that the science would break this way, because it wasn't obvious that there would be anti-aging genes like sirtuins that you could take advantage of, that are there to withstand stress, basically, and to withstand harsh periods, lean periods, calorie restriction, periods when there wasn't a good harvest. And I don't think we knew or could have imagined that there were specific genes that have been evolved and selected for that purpose. And now we know that. So now's the time that I think that we should jump in, rev up, and take advantage of this.
Go ahead.
Well, you have to consider the implications of what happens if we don't do this kind of work and this kind of research and try to slow aging. If we don't do anything and we continue on with this disease-specific approach, what we are facing is the prospect of rapid increases in the prevalence of frailty and disability associated with extreme old age. Individuals surviving out past the age of 85 in the year 2031, we know exactly when it's going to happen. If we don't do anything, the prevalence of these conditions will rise rapidly. Some sort of intervention that has the potential to slow aging even just a little bit, none of this six-fold increase that we see in these roundworms, but just even a 3-year or a 7-year delay in aging would have a huge effect, positive effect on quality of life.
I think there are data that show a 5 years delay in Alzheimer's disease will cut it in half in terms of its occurrence.
What have we found, I mean, just make sure I get my hands on this, what has been the normal increase in longevity from, let's say, 1901 to 2001? Over
30-year gain.
30
year. Unprecedented 30-year gain.
Average life.
Average life
expectancy.
Not maximum.
Well, why did that take place?
Well, we had vaccinations, we had public health, we
mainly
had sanitation,
had to do with disease,
some nutrition,
dealing with disease.
And dealing with disease. And since 1950 also, 60% reduction in deaths from heart disease and stroke, which made a difference.
But it's principally from saving the young.
Absolutely.
Reducing early age mortality.
Well, but about 20% is from age 65.
In the latter part of the 20th century.
In the latter part of the 20th century.
Right. Right. Now, I want to do this through specifics, and I want Paul to jump in with me. Tell me what you are working on. Tell me about these rhesus monkeys and what they're telling you.
So we have a study in rhesus monkeys. They have an average lifespan normally of about 27 years and a maximum lifespan of 40 years. The animals were subjected to caloric restrictions in 1989 at about 10 years of age.
Now, what do you mean by caloric restrictions in this
A
case?
30% reduction of calorie intake gradually imposed, and the reduction was based on each individual animal's baseline intake. You know, some are big eaters, some are not so big eaters. So it was tailored to each individual animal, and of course there's a control group. We added additional animals in 1994, but basically the animals have, in the oldest group are about 25 to 32 years of age now, and looking at the total mortality of our population, which initially was 78 animals, half on the restricted diet and half controls, we're starting to see a survival advantage for the monkeys on caloric restriction. We're also seeing visual evidence that they're aging at a slower rate. They basically look better. We've seen a complete protection against type 2 diabetes in our restricted animals, whereas it typically afflicts about 40% of the control population.
With the those that are having a 30% reduction in caloric intake, there's no diabetes?
No diabetes. Their caloric restriction is an opposite state of diabetes. Then you have high circulating glucose and insulin, and the insulin doesn't work very well. It's just the opposite with caloric restriction. We've also observed to date a reduction in tumor incidence in the monkeys on caloric restriction, with colon cancer being the predominant tumor. So the animals are reduced in calorie intake, as we just said, by 30%, but strikingly their body fat is down by 70%. And work we've done in mice would also suggest that there are fundamental changes in the body fat in the calorie-restricted animals in a biological sense, and the links between obesity and disease, a very hot area now, concerns pro-inflammation factors released from adipose tissue. And when we've looked at adipose tissue in mice and done analysis of the expression of thousands of genes, we see that one of the largest classes of genes that's affected by caloric restriction in adipose tissue is a down regulation or a lowered expression of 55 genes that are involved in inflammation. And we think that this may be very important in opposing the broad spectrum of diseases that caloric restriction does.
What about the numbers? Obviously these are very difficult experiments to do very long term.
Yes.
Do you get sufficient numbers to feel confident about all your conclusions?
The study started in 1989, a year before I got to Madison, and there were 15 controls and 15 restricted monkeys, and I felt very nervous in terms of statistical power. So we turned it into a larger NIH grant called a program project and added an additional 46 monkeys in 1994. And we've had the blessings of our statisticians that we're okay.
You're okay. With mice, of course, you can do lots more, so that's much less of an issue.
We typically, in longevity studies in mice, do 50 to 60 per group in those studies.
So why aren't you doing human longevity studies with caloric restriction?
They're not
part of the primate center, but...
Well, the notion of doing longevity studies in humans, that's, the monkey thing is hard enough to think about the life